Hey everybody, today I'm going to talk to you about the ODU Monarch 4 payload. The goal of the Monarch 4 payload is to measure radio noise interference during flight using a software-defined radio. During the flight, we'll also be collecting telemetry data to create a noise map post-flight, or matching out the different signal strengths that we find with our generalized and approximated altitude and flight condition. The mission was chosen because a lot of previous ODU RockSat-C missions had a radio experiment, either as sort of a B experiment or just a, hey, let's try this while we've got the opportunity. Our primary focus was the radio experiment and the communications required for a payload. The payload uses a receiver-defined active signals in different frequencies, very similar to a spectrum analyzer. The mission objectives: to develop a better understanding of the noise requirements for sounding rocket launch at Wallops Island. We'd like to collect data to verify the previously existing RF noise expectations during a launch. And above all, get undergraduate students at Old Dominion involved in aerospace related projects. On the RF side, for our expected results, we expect to see a noticeable change in the signals present during flight at different altitudes. We expect to see a pretty much complete elimination of low frequency signals once in the higher parts of the atmosphere, while at the same time we should see a persistence in the higher frequency signals during the launch at almost any altitude. And this is a picture of our payload as we get into the payload overview. The payload was sort of designed twice. It was designed once in person in the 2019-2020 semesters. And then it was designed over Zoom in the fall 2020, and then onward in 2021. And that was mostly down to COVID. There was a shift into the design of the payload because a lot of our lab resources and things were taken away from us once the COVID situation happened. So on the left, you can see like a quick little diagram of what our original payload was supposed to look like. And as we get into it, you'll notice that that's not exactly what happened. And then on the right is a design of our radio antenna. So just real quick, for anyone who's looking to design a payload or a satellite or anything that they want to work on, it's always best to start with a payload block diagram. This is a really great way to plan out all the different components of your payload and figure out how you're going to meet those requirements. So mechanically, the payload is a half caster with two separate levels, providing just enough surface area to mount all of the needed components. These are typical Lexan plates that you see in a lot of RockOn and RockSat-C payloads. And we use brackets to hold components together. Things like batteries or the radio don't have mounting holes like a lot of PCBs do, so we made custom 3D printed brackets. We also use standoffs to separate the plates, and sometimes use standoffs to separate PCBs off the plates. Electrically, there's a lot of different components that need to all work together at once. We use an Arduino to interface with the sensors that use the I2C protocol. We use a Raspberry Pi to drive the radio through USB and then collect the Arduino serial output. The Raspberry Pi sort of acts like our brain of the operations. We use an RTL SDR dongle, the receiver-only software-defined radio, to collect our radio signals. That then also connects to our antenna. We use lithium batteries to power the payload and custom PCBs to interface the batteries to the payload correctly. There are a lot of requirements that one must do to be able to launch a payload, and you won't be able to just connect your lithium batteries to your Raspberry Pi and call it a day. You need some sort of interface there. Some lessons learned: verify your mounting structure. Even though you design a structure and you think that it's going to hold up during vibrations testing because you have some experience here, that's not always the case. Hot glue is your friend. Expect to have multiple design iterations for your PCBs. Very rarely does a mechanical design work on the first go, and that same principle follows for electrical designs. If you're designing something, expect to have iterations. Cheap radios also do work. If you're looking to do a radio experiment and maybe you don't have the money to buy a very fancy USRP, cheap radios are an option and they do work great. And then finally, be wary of 3D printed brackets. If you're mechanically inclined and you like to 3D print things, be aware that a 3D printed bracket may not always react the way you think it does, and things like layer height and print adhesion and all that really matter when you're designing a structural part. In conclusion, the past 2 years have been a fantastic learning experience, and we want to give a special thank you to the Virginia Space Grant Consortium for funding our launch, the ODU Engineering Department for funding our payload build, all 24 students who helped develop the payload either as volunteers or as senior design students over the 2-year period. We'd like to thank Dr. Popescu for advising and guiding the project, and the Colorado Space Grant Consortium for being so flexible and understanding over the past 2 years. I hope this has been a good little rundown of the ODU payload, and thank you all for listening.